Welcome to a new video in the first video in block 2 of TBMT 42. So in the previous block, we learned basically how to formulate these type of differential equation based models. We looked at some different ways of representing the models, like reaction based kinetics and various circuit based type of models. And also looked at some other alternatives than what we see here, which is an ODE model in state space form. But essentially, we learned to formulate models, to simulate models, and to analyze the models as themselves, so to say, just to analyze stability and that type of stuff. Now, we will do the things that the people in the chaos community and the people in the non-dynamics community do way too seldom, in my opinion, which is to consider data. So here we have some data. We have some data points here, and this is probably as a function of time here. So the question is how to combine these two things, the data and the model, to learn about the system. And in this particular video, we will look at how to estimate the parameters. So those parameters that are like the Km and Vmax and so on, conductances. We need to have values for those. And if you don't have them from before, which you often don't, then you need to estimate them from data. And then you need to formulate an estimation problem. So this is an optimization problem here. We should minimize over the parameters. So we are today going to learn to write up this minimization problem. So the first we'll do is just to formulate y hat and the standard cost function and intuitively understand the different components in that. And once we have the cost function, we can formulate this estimation problem, this arg mean type of problem. And we'll see that this is perfectly viable for normal parameters, but we'll also realize that there is an issue if one of the parameters that you want to estimate is the sigma, which is the uncertainty of the measurement data. Then we need to have a more general objective function than the normal cost function, and that is the likelihood function. So we'll get we'll do some derivation for the likelihood function in some common in a common situation, and then we will use the likelihood function to create an estimation problem that also works if you don't know the value of sigma. Okay, let's go. So we have some kind of state, we have some kind of model, we have learned how to simulate the state. And now we need to create a measurement equation. I alluded to this a little bit in block 1, but now this is front and center, the measurement equation. So this says, given some state, which might be the concentration of something, it might be the current, it might be the amount, it might be the voltage, something that is you have a differential equation for. That's what X is. You have some parameters, which are the unknown constants in the model. These typically don't change over time. And then you have some kind of input, which is what you do to the system. So here we see we have a sort of input-output relationship. So the input here is what you do. Maybe you give insulin to it, or maybe you stimulate it with electrically, or you give a drug, or you give a meal, or you do something to the system. That's you. And then we have the output here. And this is the total output, the one that you measure. And this is constructed by two parts. One is a deterministic part, which is given by the simulation only. And the other part here is given by some kind of random variable, which means that each time you do a measurement, you will get a slightly different value because you have measurement noise simply. And this measurement noise here, this random variable, is scaled with some h function, which often is just 1. But sometimes it's something else. And if this one depends on x, then you typically talk about multiplicative noise. So the sort of the size of the x will somehow scale the size of the noise. If they are independent, then and if this is just 1, then it's additive noise. But if this somehow is also dependent on x, then you typically talk about multiplicative noise of some kind. Okay, so the standard way of estimating the parameters is to use the weighted least square cost function. You have probably encountered this in previous courses, but we'll go through it now, have this as a basis. So the unit, the sort of primary atom, so to say, of formulating this this cost function is to look at something called the residuals, which is the difference between the simulated and the experimental value at each time point. So again, the simulated part is the y hat, this one here. This one depends on the parameters. So if you forget which one is which, the data doesn't depend on the parameters, only the simulated, the deterministic part, the one that comes from the simulation. This one depends on the parameters. And then you take minus y, which is the measurement data. So the difference between y and y hat, that's called the residual. And then these residuals, you basically sum them up, but you take the square of them. And that's essentially what makes up this cost function. So this is one way that it's often written up. There are some different options. But somehow you want to make sure that the residuals, the distance between y and y hat, the distance between the predicted value and the actual measured value, that distance is a distance which is always positive, because you want the cost to add up all of those distances. So you don't care if the prediction is wrong because it's under or if it's over. You just care if it's different from the measured value. So here, instead of having the square, you can have the absolute value. You could potentially also have other things. Sometimes you work with the L1 norm, for instance. But this is the sort of L2 norm here, which is the square. And then you sum all of these squared residuals together. So you take it for all the data points, not only for one, but you take for all. So this is the summation. And then here comes the sigma, which is the uncertainty of the measurement data. This is the standard deviation of the measurement uncertainty. And you divide with that, because if you have a low sigma, you have a well-determined data point. And that means that you divide with a small number, which means that this term here in the summation will be a big number. So low uncertainty in the data means that a distance from the data is more important than if sigma is high. That's what this one does, and we'll look on the next slide a little bit more what that means. And then if you want, you can also take the square root of this, so it doesn't grow so much. So sometimes this can be very, very big numbers, and then it might be good to take the square root. And sometimes you also divide by the number of data points to have it more independent of the number of data points. So here we didn't do that. So there are some different options, but the essence is that you take the square, or you take the sort of some kind of positive version of the residuals. You normalize it with the uncertainty of the measurement data, and then you sum it up. That's sort of the essence of the standard least square cost function. So let's look at a very small example. Here we have time on the x-axis, and we have the concentration of glucose, which is what we can measure on the y-axis. Here we have the cost function again, and here we have this x here is the measured data point, y without the hat, at time point 1. And here we have the simulated one. So the simulated line is here, and for each point where we have both a simulation and a measurement data, we can look at the difference. And the data point here has an uncertainty, and that is reflected here. So this is 2 sigmas, so it's 1 sigma in this direction and 1 sigma in this direction. So that's the standard deviation. Okay, so let's just observe here that the residual then is the distance between the observed data point and the simulated. So these are the ones that in the cost function, you add up these. And when you optimize it, you want them to be as small as possible. And so you take the square of this and you divide by sigma square, and then you add up all of those. And now here you see that the sigma is different. So here it's about the same size, but here it's much, much bigger. So if we look here at time point 3, then we see that the data point is down here and the simulated value is below here. So here the residual will be negative, but the distance is the only thing that matters because we take the square. But here the distance is slightly bigger, as you see. It's bigger here than it is down here. But since we divide by sigma, it's not the absolute distance that matters in the cost function. It's the distance in relation to the sigma. So here we see that the simulated data point is 2 sigmas away from the measured data point. So the measured and simulated are around 2 sigmas away from each other. So here the ratio between the residual and the sigma is around 2. So you take that square. So this particular time will be around 4. However, here it's less than 1 sigma. So even though the residual is bigger, the distance is less than 1 sigma. So here the ratio between y minus y hat, the residual, and sigma is less than 1. So if you take that square, that's also less than 1. So in this particular case, the contribution to the cost function is 4, but here it is less than 1. So this is a much more important deviation because you're much more sure of this measurement here. This measurement data point, you're not really sure what you measured because it's so uncertain. So you should take less account for this one. This should not be as important in the cost function. But this one here, you are fairly well determined that this is the value that you have. So this should be more important. And that's why you have this division by sigma. Okay, so that was the intuitive understanding. Let's now look at how we formulate the actual optimization problem. So let's look first at just estimating normal parameters, the type of parameters that we have encountered so far. So the rate constants and the volumes and the conductances or compliances and inductances and sort of all of the constants that you have in the model. The initial conditions, which is where you start, those might be unknown, and then you need to estimate those, and the scaling parameters, so the parameters that appear explicitly in the measurement equation. So let's consider the situation that we need to estimate those, but the measurement uncertainty, the sigma, is known. Then we just minimize over sigma. So we want to minimize this cost function that we looked at. So we want to see for which parameter combination of all these values do we have the smallest cost as possible. So the best agreement with the data, the smallest distance between the data and the simulated points. So we want to minimize V, but we don't want to have the smallest cost. We want to have the P, and that's why you say the argument. So arg means that what we want to do is that we want to minimize over P. So we want to have the smallest cost function, but we don't want to have the cost back. We want to have the P that gives the smallest. So that is the estimated parameter P hat here. So this is the optimization problem that we in the next 2 videos will learn how to solve. But for now, we will find an alternative way to formulate this estimation problem. And that is especially for those cases where you have some slightly more complicated situations. For instance, if you want to estimate the measurement uncertainty, the sigmas, you cannot do like this. You cannot just treat it as a normal parameter. So you just sort of minimize with respect to sigma, and then you use the normal cost function, and then you just take the sigma that gives the smallest value. And the reason for that is that you divide by sigma. So since you divide by sigma, you get the smaller cost function, the bigger the sigma. So just putting sigma go to infinity, then V will go to 0. So this is, of course, not the solution. Sigma should not be infinity. That's not the right answer. And the reason why it's not the right answer is that we are not using the real cost function, so the real thing that you actually should optimize. So what we should optimize in this situation and in other situations where you have a more complicated situation is the likelihood function. This is what you really should optimize. Sometimes they are the same, but sometimes they are not. So the likelihood function describes the probability of the data for some given parameters. So let's here, just to understand how this is constructed, let's just assume that the data was generated with some simulation with some true parameters, P0 here. So this doesn't mean the exponent, this just means that it's zero. This is a common way to write that these are the true parameters. So then y would be equal to y hat for some true parameters here, and plus some noise term here. And this noise term that we have here, that would be the innovation that we sometimes call it, and that is a random number that is drawn from typically a normal distribution with mean 0 and standard deviation sigma. So this is the most common assumption. It's not always the right assumption, but it's a very common assumption. So with this situation, then the probability of measuring a value y here will simply be this mean value, which is the deterministic simulated value, plus a normal distribution. Or said in another way, it's a normal distribution where the mean of the normal distribution is y hat. So in this expression here, the probability of getting a value y is some coefficient here, and then you have the exponent to the minus, and here you have this y minus y hat again. So, and the reason why it's y hat here is that the normal distribution of y is not centered around 0, but it's centered around y hat. Okay, so this is just the definition of a normal distribution. But this is just for one data point. So if you have a time series, so you measure, say that you measured 3 variables, you measure glucose and lactate and the volume of the cell or something like this, if the volume changes over time. And you do that for n time points, maybe 10 time points. Then the total probability, if you assume that these noise terms here are independent, which you typically do, then you simply multiply them together. So the probability of the combination is the individual probabilities times each other. So here, this is just the multiplication or overall of the measurement variables and overall the data points for each variable. So this is just product over all the data points. This is the same coefficient here again. And here we have y minus y hat, where we specify that the y and the y hat and the sigma comes from a specific data point. So you remember in the previous slide, we had these 3 data points, 3 time points for one variable, glucose. Okay, so this is the likelihood function in the situation where we have independent, additive, and normally distributed noise, which is a very common situation, at least that you assume that you have. So let's now see how we can go from this function here to something that we can put in a cost function. So this probability will actually depend on the parameters, because y hat here depends on the parameters. So for different parameters, we'll have different y hats, and different y hats. So if we have the true, then the data will be very probable, because it's just the noise. But if you have a very bad simulation, then the data will sort of not be very probable. It's quite improbable that you have those data. So you want here to have the parameters where the data are as likely as possible. And typically, you do that by maximizing the likelihood function, or easier, the logarithm of the likelihood function. And if you take the logarithm of the likelihood function, then these products will become additions, so they get different terms. So these two are the coefficient, and this is this exponent. And the exponent, when you take the logarithm, it just falls down. So this is what stands in the exponent. So this is y minus y hat, and here again, y hat depends on the parameter, and you divide by sigma. So this is the first term of the logarithm of the likelihood function. So this is just a normal cost function that we looked at before. Y minus y hat summed over all the data points. And now this leading coefficient, the one that was before the exponential, now this one appears. And here, this is two things. One is just 2 pi, which doesn't matter at all. But the other one is sigma. So here we see that we have a second term, which is sigma. And here it's so that if you know sigma, so you're not optimizing over sigma, but sigma is always the same value, then this term will just be a constant, and when you optimize, you will sort of not change the value of sigma. So then you just optimize over the parameters, and then this term is always the same. So then the optimum for this combined function and just the cost function here, the old cost function, will be the same, because this one will only shift the value of the likelihood up and down, but it will not sort of distort it. But this one here, if you don't know the sigma, so you're also varying this over sigma, then depending on the value of sigma, you will get a different likelihood or log likelihood. So this is always constant, but this one depends on sigma. So that's the key thing. That means that now we can formulate another optimization problem where we minimize over P and over sigma, and we want the argument over both P and sigma. So this formula here, if we instead use the likelihood function or the logarithm of the likelihood function, then we will have an estimated correct value for sigma. If the model structure is correct, it will be correct. So we can understand here that before it was so that the maximum likelihood function was just by having as or the maximum cost function was just by the minimum cost function, which is the maximum of the likelihood, is given by just as big numbers as you can get for sigma, because then this will get smaller. But if you also have this term, then you see that this one will get smaller, but this one gets bigger. So it's a trade-off. So there is a value of sigma and P that together gives the lowest value of all of these guys up here, and the sum here will also be as small as possible. So therefore they will depend on each other, and you can sort of treat this as a normal parameter. Okay, so that's it. That's the sort of the general way of formulating an optimization problem to get the parameters, including also the sigma. So you maximize the likelihood function, you make the data as probable as possible. And if you don't want to have, if you have a sort of easy problem where it's just normal parameters and sigma is known, then you can just minimize the cost function. Okay, that's it for this video.